I made a diagram last summer of the trigonometric functions, and I thought I would complete it for you, and I've been trying to get it run to your head because I'm a little slow at looking at my paper and putting it on the board. But when I finish it, I think it's going to be useful to you. But remember then, we're always starting with universe, and then we're subdividing. So we start with a sphere. Our geometry begins with a sphere, or at least with a system. And a sphere is simply a high frequency structural system. The sphere is a high frequency structural system, all triangulated, and so it'd be approximately unit radius, high frequency structural system. And I'm going to go through some of the arguments of the geometers of the early days about how you play a game of geometry in Egypt and Greece, which is really worth our feeling here, because they took for granted a flat Earth, so they're starting on a plane. But if I'm going to play the game in starting with totality, I've got to say, what do I have to prove things, so forth. I think you're going to find it comes out really very satisfactory. So I'll complete my picture here. This is then a section through our sphere, radius, and we just make a working assumption. Radius is 1. It is sub-frequency. It's just unity. Radius unity, and I have the angle that is considered is called theta, and it's from here to here, and this is half theta. It's A is half theta, and it gives you can have the right to have a perpendicular bisector of the chord, so we can assume this 90-degree angle. So it's the right angle that out of which we then come into trigonometric functioning. I've spoken in public for years and years and years. I've never drank water at speaking till I came here. And always, because I was a long-distance runner, and I found that nature makes her own juices and has her second winds and things, and I know that you don't drink water when you're running, and you don't drink water when you let nature do that, so that I'm a little puzzled by, I think this is a tail end of a cold. I had a very bad cold late in December, and came back from Europe I've been speaking in Europe, and I came back to speak here in Philadelphia, and I literally couldn't speak for the first time that ever happened to me. And there's some kind of tail end of something going on there. I don't know what it is. I'm sorry about it. Now, coming back to our diagram, I want to complete it. It'll just take me a little bit to do so. I want to make a green line here, and I want to have so many things to keep in your fingers, and an orange line here vertically, and I have a red line B, ER, right. This line comes in. E up here. And I'm going to make a diagram of that here. I just started making a side picture what's in the diagram on the side. That seemed to be useful. Now, what message is missing here? There's an M missing here. No, it's an M. Hope that's as clear as it goes there. Now, I think everything is on here. And so we're talking about a trigonometric angle. This is angle theta. And so she's always isosceles, and then to get the advantage of a right triangle and all the laws of right triangles, we then have this perpendicular to the chord, and we get the half theta, which is A. And that's the angle we always do checking. This is what we're checking up on all the time. And so I'm now going to mark what these are. This orange one over here is FD. F. And goes down to D here. So FD is cotangent. It actually says all these things right on the diagram, but I sort of separate them out too. F and O, always center of the sphere, and this is F and O, and it is your cosecant. And the red one here has the E and O for me here. This is your secant. And then E to B is tangent. And M to K is the famous sine, S-I-N-E. And this is your cosine. Those two sides of the right triangle, the sine, cosine. And so they are of this famous angle theta, half theta, A, when we look at it. Okay? I think this makes things look fairly simple for you in looking up, you know, what you're really finding out. The data you'll get will be either expressed in degrees, minutes. It could be it could be sometimes they do it in hundredths of a degree, and that you can be done in radians and so forth. But it does make a difference which language you use. You're multiplying and subtracting. So your formulas will be multiplying and dividing one of these things times another all the way through to find out various trigonometric phenomena. But I think this is quite a simple diagram, and it was not given to me when I was young, so that I really worked on some that really have it. It seemed to me pretty easy. Now, I'd like to think about the game of geometry as played by the Greeks and the Egyptians. They played their game with a straight edge dividers, so that's so your dividers, you can strike circles, or you can measure distances, and straight edge and dividers. And you had to demonstrate that an unfamiliar geometrical form consists of demonstrated forms in terms of your original construction. But whereas they played a game of making using a straight edge, then taking any point on the line, put the dividers on there, and they can strike a circle, and it would cross the straight line at 2 points, and those would be the radii, and you know they're equal to one another. and they're half in diameter. This is a fairly simple game. They could then, from where the circle crossed the straight line, they could go out there with the dividers to the end, put the dividers on the crossing point, and break into the circle from either end. And they never could prove that the space between was the radius. Therefore, they never assumed the equilateral triangle. Starting from a plane, you get into that trouble. And I don't get in that trouble. I'm sure there's one reason why the 60-degreeness has not gone into the popular game of geometry. The radius seems to be self-evident, but that's all. And you knew that the dividers seemed to span exactly, but you couldn't prove it. So I'm now going to start, and I'm going to say I'm working on a plane. I'm going to make a sphere. I have my dividers, I have a point in the universe, and I have a radius going in all directions. Okay? So I'm now got a surface to work on, and I know all of that surface is equidistant from a given point. Now I'm going to take any point on the surface of the sphere, and I'm going to strike a circle on the surface of the sphere. You'll not call it a lesser circle, but we know that every point in that circle is equidistant from that point on the sphere, on the outside of the sphere. We also know that every point on that circle is equidistant from the center of the sphere. That's quite nice. So now we have quite a little two kinds of things. We have a radius of the sphere that is known, and we have the radius of the surface circle that is known. They're both the same divider. I can now then take any point on the surface circle and dividers and strike another point on that same circle. You see that? Now, I'm going to go to more or less the opposite side of the circle. Doesn't make any difference where I come on there. Some other part of the lesser circle. I find quite quickly with my dividers that the lesser circle really seems to consist of quite a number of increments of this. So I'm going to go any opposite side where it doesn't make a difference, and just take another point on the lesser circle on the surface, put my dividers on that, and strike against the lesser circle again. I got two increments. They are, just look at the globe of the world, and I got a circle up here, but this one here, say, which is about the same as radius of it, and I come to an arbitrary point out here, and I strike on the circle here. I now know what that distance is. Quite clearly, if I try stepping my dividers around, it takes quite a few divisions. So all I have to do is to go to the opposite side to pick any point I want, somewhere in here, dividers, and strike another. I now get two arc sections of that lesser circle. And I know our radius, I have a unit distance now, which is the original radius of a sphere, and the radius of the circle on the surface. I got two increments here which are exactly the same. I'm now going to run a line back to the center surface point here and two lines from there. This now gives me two triangles on the surface with that I know the radii of those, the edges of those triangles are all equilateral. I know I've got two equilateral triangles with a common apex at this center of the surface circle, which goes down to the center of the sphere, and we know they're all equidistant. So then I was able to take those, you may remember the way I made the four great circles. Yes, it kind of looks kind of familiar because I want you to look, for instance, here is the sphere defined. I got up to the point here, and I struck a circle Now I've got these two units here, and all I've got to do with them is to remember how I made them. What I have is this, and these are all radii, everything is radii in here as originally constructed. So nothing to stop me rotating this around the radii and coming down like that. Now I've opened up I know all those edges are identical in length, and they're all freely rotatable about this. So I now have a hexagon. These are all chorded. I'm able to extract the hexagon then from the sphere and really know what it is. Is that comfortable to all of you? Remember how I did? I first used my dividers starting at this point and developing a sphere. Omnidirectional from a point. And then from that, I go to the surface of it, and I know every point on the surface is equidistant, so take a point on the surface, and I struck this circle out here, a surface circle. And I took any point on that surface circle and struck over here and got that length. So I've got a chord. This is a chord. This is I struck that. I know all those 3 points are equidistant from one another now. It's all constructed that way by my dividers. Same thing over here. And they don't have to be, diametrically opposite. Please understand, because you've proven with your dividers going around that this circle broke up into much more than 2. It broke up into approximately into 6. So I just take really quite randomly, because this is a hinge. So these are able to hinge exactly like that. So I now have constructed 2 tetrahedra, edge to edge. I'm able to open the 2 tetrahedra out in the flat, and now I find them actually consisting. Then now I know I have a hexagon, which every part has been constructed by the dividers, which is privilege of starting with a whole and working to the particular that you couldn't get to. This is synergy. The behavior of that whole that did not permit it if you tried to start with a part. Is anybody here to find any geometrical fault with what I'm saying? Janet, you're thinking good and hard. Does it seem all right? Good. I haven't found anybody who's ever found any real fault with it, but now I'm really privileged to think tetrahedra, and I humanly understand how from there on I can reestablish these 4 great circles. So making these 4 great circles really part of my game of geometry. It is a very beautiful thing that you had the circle, and so everything is absolutely superbly proven all the way through. Now I have a very nice kind of a geometrical situation where I can then use the diagonals of these squares and so forth. And I can get my x, y, z coordinates. Everything that you're familiar with can come out of it from now on in those great circlings I give you. So all the important coordinates that man has ever used are manifest here and constructed so that if you want to take things out in the flat, you're extremely comfortable about what the increments are. There was, doing spherical trigonometry, which is dealing in the laws of that right triangle. It's a beautiful thing, right triangle, because by doing so, you have one thing that is known. That's really great. And then you found that there was sort of constant variation between the whole of it added up to 180, so that if I make one angle smaller of the non-right angle, the other is going to be larger, and the sum total always going to be 90 degrees. So you've got 2 very important things known. You've got a known 90 degrees, you've got known some of the other 2 add up to 90. And they're going to be varying, they're going to co-vary with absolute arithmetical accuracy. So this brought about the development of the trigonometric tables. as I gave you yesterday, the maximum variation you really can get to is then where you have an isosceles, 90 degrees, and it's an isosceles, and the two corners are 45 each. So 45 is in as much as they co-vary, 45, the largest gets to be 45, the smallest gets to be 45. And as much you learn that, so all you have to know from now on is up to 45. That's why I gave you yesterday all the prime numbers. There's some people who spoke to me, amongst you, about the prime numbers, not quite certain why I carried 2 and others to 2 to the 12th power and 3 to the 8th power and so forth. I simply find that there is then trisecting that goes on. You need 3-ness and 2-ness, and as you get into multiplications, you need a whole lot of 2-ness of the prime number 2 to give you great flexibility in complex computations. But you don't have very often that the prime number 43 comes in. One of that is enough to be sure to accommodate, and if it's in the dividend, it will accommodate all of it. But there's quite a number of recurrences, the 2s and the 3s and the 5s, and you can understand that quite readily. That's why I have many powers of those numbers. And I did not really know, and I haven't got to the control of it yet, how many you would need very certainly. But what I did was to keep going through and developing, multiplying the powers times themselves, and sometimes doubling and tripling, to see if I came to interesting numbers. And if you look at your book, Synergetics, you'll find that every so often the numbers are very regular, and suddenly comes out absolutely 9 million, whatever it is, something incredibly beautiful, simple number. And you say, nature's come in, she's clicked here. She's deliberately made it very simple, sublimely simple. So I began to give these names what are called sublimely rememberable comprehensive dividends. I kept exploring and multiplying, been doing this for years and years, and every so often she came in phase, so I've got a listing of those. I used to do all these things longhand. There wasn't any computer to do it with. So I began to get used to the rate at which you accumulate, where you have to put something over the next column. So I began then to see that whereas things looked a little messy, it's simply because there was a spilling only to the left. If you had some way to spill right as well, you might keep up the symmetry. But up to the time you get up to more than 10, so number 7 is what you saw, the 1, 3, 3, 1, then the next one goes 1, 2, 3, so 5 in the middle. It's a very interesting compound, but suddenly goes beyond 10, then it begins to spill over, and then the symmetry tends to go. I'm so familiar with that that makes it, the number I recited to you yesterday is comfortable to me, and I could show you exactly incredible, beautiful cross symmetry, the two sides of it, but some spillings over, and I'm used to how they do, so that's why I can remember it so readily. This is the largest one that I have come to. It is interesting, having done those longhand, I can't tell you how long it used to take to do it and check yourself. Now that we do have a computer, I got some of the big university computers to work, and all my figures have been checked. This is absolutely check figure, and I feel very comfortable about it now. In the early days of navigation, then, because you could solve problems with triangles, and there was yourself and 2 stars, or there was your ship and the horizon and the star. There were three time and again to give you some kind of effects. So obviously, they gave you some angular control, and you could get to converging lines of angles. One of the great significances of the models I was giving you to make, and the significance of people not getting things right, was that they didn't tend to have them approached like this, because the perpendicular, you're thinking about perpendiculars of 2 quadrangles seem to fit this way. You're trying to match surfaces by parallel motion rather than by convergence. So there was one where one side reads more than the other, and you find, of course, going this way, of course it does. But we do not. The navigator does think in convergent angles, and I find the landsman thinking in parallel angles. He thinks parallels all the time. It's way over balanced on thinking about the rectilinearity of X, Y, Z, and just the word three-dimensional. I've never seen a scientist go to the board doing a problem when he didn't say superscript 3 always says cube, or superscript 2 just says square. If it's superscript 4, then he says fourth power. But he does not say second power, third power. He's got an absolute identity of that squaring and the cubing. So part of my synergetics has really been, I've had a hard time getting on with people because they still come back to talking three dimensions. The word is in there, even though they concede some of the points I make, they go back to three-dimensional thinking. So when we have this lovely convergence, and the convergence, it does bring you to nuclei. There was nothing in the geometry of the Greeks, there was nucleus. There was no inherent center. There was always boundaries. It's out of a game of boundaries. And as I said, they always then accredited only the area that was bound by, and the rest of the universe didn't count. So they had an automatic bias and a really myopic bias of looking at things in a small way. I hope you like doing with me what I am doing. I was trying to understand the significance of the fixation, the conditioned reflexes that are heightened, very greatly heightened by the educational system, that make you look at things in a myopic way, rather than the beautiful complementaries that are always there. So you can always think in the complementaries, and they're equally rational, and give you a chance then to be very comprehensive and to be synergetic. Now, with navigation, I'm sure many a navigator lost tools that he had, a great sea going on and all things washed overboard. And so the navigator tries to contrive to do things in a very simple way, so those Maori and the Pacific Naga sailormen, so I said, were naked. They had things around they could have things around their wrists and arms and the neck that wouldn't come off. That was pretty useful. And they could have things in their ears. So these are the only pockets they had. The more I learn, the more I'm certain that probably those rings in the necks of the people who thought of being sort of such simple people that they're just children that sort of decorate themselves in some superstitious way. I think those rings were literally like the abacus. These are things that slide up and down in the neck, the counting devices. And it could be that the person who's wearing it doesn't necessarily know that that's what the navigator uses. Very useful to have different people on board having different kinds of equipment if you're the navigator. So you have several pockets on different people's necks and arms and fingers. Now, we come to days of fancier ships and big ribbed ships, big bellied ships, and getting to great navigation, circumnavigation, such as Magellan, Drake, and there are storms and the battles and the things get lost. What are the minimum number of things that the navigator had to have with him to make calculations on how in relation to his observations? And part of the trick of helping that navigator was try to simplify the number of things you need. Certainly, with calculations have been made, it was very important to have tables of calculations been made, and those were made by monks. And for really up to the time of the computer coming in, yes, even in time of World War II, with the Great Depression of 1929 and the 30s, the big government, the kind of tables that I first had myself were all monks' tables, and everybody knew there were some errors in them, and there are formulas that were carried out, but also with all these prime numbers washing around, making numbers really where you were very arbitrary about whether you would call it the next higher number or not, which side of the fraction to go, and how many places can you really carry out things with any degree of real accuracy. What did you really know? So 5-place and 6-place tables, 5-place tables by World War I, that's about all you had really. Then there was all these, the WPA in America, Mathematics Project, put a great many mathematicians and scientists to work. And they did get up to 6 places. Strangely enough, the English and the Germans jointly, the English Navy and the German Navy, with Goering's idea, compounded their efforts in those countries developing better trigonometric tables. And they're what's called the Edwards, you and I could get today called Edwards tables, but these were developed by those two, and Goering, with his Lufthansa, wanted much better calculating capability and much swifter calculation to be made in air observations. He really did get the English to cooperate. When the war came, then they broke company. But the Germans printed this work. And after World War II, the American alien property custodian, when the United States came into Berlin, one of the things that the Americans got hold of were the German trigonometric tables. And they were published by a firm in Ann Arbor, Michigan, and it's called the Edwards table. And those are good for 7 places of accuracy. And when I was able to afford that, this book was quite expensive. I was absolutely broke. I got my Edwards table as soon as I could. And that was done in increments of seconds, rather than where you had to interpolate between seconds and minutes and so forth up to the degrees. So interpolation was a very important part. But I've done some much trigonometric function calculations that I'm terribly sensitive to the errors I have found as I would go, because in getting into geodesic domes, where I saw that I really could get into comprehensive enclosure, and I could get into omnitriangulated, and I could get into tensegrity. But I saw that if I'm going to bring three struts together in space, I really got to know very accurately. 2 of them might get there, the other one overreaches them, and now trying to bring 5 and 6, they're going to be in very great redundancy. I really had to have very great accuracy. In the building world, you'd be interested just to talk about the world that I had been in when I built those 240 buildings after World War II. In dimensioning of buildings even today, as a workman put together, a 1/4 inch is a perfectly good tolerance. But if you're building bearings for an automobile, you can't have anything like that, so the automobiles men get down to 10,000 of an inch. In building airplanes today and the space rocketry, where mild variations, enormous velocity can build in errors, they're dealing in a millionth of an inch. But the building world is still a 1/4 inch kind of stuff. I couldn't have any such nonsense as that when I really going to get into geodesics. I was out to see how I really could reduce stresses and forces. To give you a little example of the significance of what I'm talking about, I was asked to design the dome over the Ford Rotunda building in Detroit for the 50th anniversary of the Ford Motor Company. Old Henry Ford liked his Rotunda building very, very much. He used it for Chicago World's Fair. He'd had it moved after the Chicago World's Fair to Detroit, and it was the reception building for the Ford Motor Empire. But he wanted a dome over it. And so his grandson thought for one of the items of the 50th anniversary, it'd be very nice to have a dome put over it. The Ford engineers found that it was a World's Fair structure, very light steel work, and that it could not take the load of the dead weight of a dome. It could theoretically take the snow loads, but the best known ways to build domes, they were what called radial arch domes by this time, with steel. The weights ran way over what the building could take, and they had to really rebuild the whole building. And young Henry was very disappointed, and his cousin, another Ford, had heard about my geodesics and familiar with it, and suggested that they ask me to come out and see what I could do. So I suddenly had a call from the Ford Motor Company, and as far as I'm concerned, I was really very much of an unknown at this time, and said could come out, and I thought somebody was kidding me. So they come out to Detroit, and sure enough, they got a very fancy automobile rushing out to Rotunda, looking it over. And they said, could I put a dome over it? And I said, yeah. And said, could you make some calculation what it would weigh? And so I did, and the calculations, they didn't tell me the dilemma, and my calculation came out well within the tolerance limits. So they decided to go ahead with me. And the engineers and the Ford operating management were tremendously skeptical of this character coming in and doing something like that. So it was a very wonderful operation. I showed you yesterday struts where you could just take sheet metal and bend it. In the world of aluminum, we'd gotten up to very high tensile strengths with World War II. Aluminums as we entered it before, we were 20,000 pounds a square inch was about it. During the war, a Japanese alloy came in, it was a 71 ST. We got up to 71,000 pounds a square inch with mild steel, 60,000, 50,000. So it was very strong. It was equivalent to the kind of strength you got in the first Brooklyn Bridge. And it had only 1/3 of the weight of the steel. So it was a very, very high advantage metal. It was I could really only get it in sheet form, and there's nothing quite so the thing that man produces in such quantity and such speed as sheet, whether sheet steel or sheet aluminum or paper. So we want to really take something he has for membranes and control environment. Sheet is very advantageous. So I found like take my sheet and with the brake, you can bend and make your angles. And we got into really quite fancy angles. They're not just an angle like that, a 60-degree angle. That's 70 degrees, 32 minutes business. And they were also, they had little secondary ribbings along the edge so that the edges of the metal would not curl and so forth. So actually it was a V like this. This way this thing's carried out its best strength. I was able to deal in a very lightweight sheet of 0.032, where you got 3 square feet of material for a pound of metal. And so I designed the dome with that. And then where the parts overlapped, they had to be riveted. It's been learned during World War II in the riveting of airplanes, with enormous production of airplanes, rivet holes were of greatest importance. So parts have been made here and parts there. Could you bring parts with holes punched in them, bring them great complexes and still have them all register and have rivets come in? Those are some of the production tricks that the Germans and English had developed. The United States inherited a lot of these techniques with extraordinary kind of controls of lights focusing on metals and so forth, and using light-sensitive things that punched and so forth. Anyway, then discovered, thinking about what kind of strength differences do you get in the airplane where you have 2 holes and they're a little off like that, and the rivet has to be then small enough so to go between the two because there's a little slack in it. Got into an enormous amount of testing and laboratory testing of the relative strengths arrived at where, as you got better registering of the 2 holes as far as the center of the holes go, and the hole sizing, and they found that the strengths went up very, very rapidly as you got greater and greater accuracy, both the positioning and the sizing of the hole and the sizing of the rivet that slid in. For a fairly simple reason, if they were sort of slop in it, it could be everything's fastened down good and tight, but the big stress on the thing, if there's a little more slop opening in this particular direction, something she starts slide, yield all the thousands that you get a little slop in this side will yield in that direction. Let's start a shearing action, things begin to go. So if shearing can't start, it's very much like having a pole that is balanced. You have a pole balanced in your finger, and there's nothing really to keep that, no effort really to keep that. Can you keep on that dead center? And if you don't, as you get off it, it takes much more effort to withstand and keep where you like it. So when I did the Ford Motor Company dome, I also found the best people in the Ford Motor Company by far were the tool men who made the mass production tools. They are the brownies of Detroit. No matter how the management, they're the ones that get things tooled up and get ready for 3 years from today when they start selling things. But they're the people who really are keen. And the tooling men liked what I did. And I designed the rivet holes for there were some thousands of these struts, and many thousands of them, some 50,000 or so. And I designed the rivet hole positionings and the rivets themselves. We kept the tolerance to a 10,000th of an inch. Now, bringing 10,000 of an inch into a big building where the quarter of an inch had been fine. You imagine the general contractors, when I faced them this, said, you can't have any nonsense like that. So I said, I have designed all the tooling. I've designed all your logistics. As general contractor, simply, I'll handle the whole thing for you. There's nothing, you really have to do nothing but just write out the checks and pay the bills. So I then had to put on a show for the Ford Motor Company in my office. I took an office in Detroit, where I gave them complete logistics of the complete design of every part, how every part was to be manufactured, how it'd be organized at the job, how it'd be assembled, the roof, what workmen would do each job, and how many there'd be. I spelled out the absolute whole thing. And the general contractor said he never had anything done like that before. This is the kind of work his estimators and engineers had to go to work and do, and he found it all done for him. So he was really very agreeably surprised. That helped me a lot. It was an operation that was very difficult because the Ford Motor Company had already been spending a lot of money getting things ready for the 50th. They had invested over $25 million in TV shows and a big show they're putting on. And so they didn't want the work they were already doing being messed up. There's something going on overhead. So I had to build a bridge across this thing, and I used a high voltage cross-continent mast flow and the top of it, with this bridge going across, introduced a hydraulic arm that went upwardly and revolved around. We mounted the dome. They were very scared about the danger of the man working here. So there's enormous steel arms that went around with a dome on it, and people could reach it from the bridge. They didn't have to go up the scaffolding anywhere. And we were able then to continually revolve the dome going up, and they keep adding on to the bottom of it from the bridge, so nobody went low, until it was all up, and then we let it down onto the actual parapet of the roof. So all that had to be calculated very accurately. There'd be no stresses in that. And the roof was not very beautifully done, so I had to really allow for all kinds of come and go, shimming of the thing. So anyway, the work that I laid out, there were a certain number then of hole patterns there were 6 prime variations, and the Ford tooling men made up Class A steel dies to stamp out the parts and to punch the holes. They were able to pre-punch the holes in the flat before they got in the bending. But everything was under such tight controls that I kept this down to a 10,000th of an inch. Now, the interesting thing is that the dome weighed exactly 1/2 what it would have weighed if it had been laid out by the best sheet metal workers in the world at the tolerance the sheet metal worker can lay out. I had absolutely these invisible tolerances. And the dome you have exactly 2 domes for one, the same amount of metal, simply by that tolerance difference. That could be that, when you get that kind of economy and inherent in competence, you really understand the reason why I would feel that I'm not putting it upon you to take some of your time to begin to get into the subject of the geometry and how we do good calculations and so forth. Now I'm going to come back to man and as a navigator going around the world, you're trusting this great ship and all the people in it, and enormous commitment to this navigator to get you from there, going in unknown seas and don't know where the rocks are, and you're sailing at night and you can't stop the wind blowing in this direction. It's a very hazardous undertaking. And so Napier in England developed some very beautiful rules in trigonometry to simplify the navigator's problems so that he couldn't make what we call a 108-degree error. because of these quadrants, X, Y, Z quadrants are going around, it's really very easy to make a plus or minus error and find yourself going exactly the opposite direction where you ought to be going. So he simplified this out, and he then developed a game of calculation trigonometrically, which you could find in Bowditch's Practical Navigator, which was the Bible of navigation for the United States Navy, for the Naval Academy, and you still find it there. But I'm going to give you these rules because I found it very useful all through the years immediately just before the Ford Motor Company Dome, a few years after. I found myself being invited all around the world to architecture schools, and whether it would be in Ghana, it would be in India, and so forth, I would have a class of students, and they would vary from 18 to possibly 30 in number. And I would teach them then all of this mathematics, and I would teach them then how we calculate geodesic domes and everything. And we would then literally organize production. I would organize the students into aeronautical production, how you develop prototypes and get into production in aeronautics, using that kind of techniques. And there was purchasing to be done and so forth. And so really got the students immediately hooked up with real life. Not only did they get hooked up with real life, but they found, time and again, we had, Cornell, the president of DuPont happened to be a friend of, he had a student, a son up there at Cornell. He was interested. One reason or another, there'd be somebody you could get in touch with, and you said, we're going to make an experiment. We really, no use in going through this without really using the most advanced materials, and we understand you have a little better clear plexiglass where it is, and these men would send you special airplane materials, so they found enormous cooperation on the part of industry, again giving enormous insights. So the students are organized in teams with purchasing agents and mathematics, head of mathematics departments, design engineering, and the production engineering, installation engineering. All the logistics are worked out, everything we did. This is what I call comprehensive anticipatory design science. You're responsible for everything. I'm responsible for how it's going to be removed and so forth. Just one last word reflectively on that Ford Motor Company dome. When they finished lowering that dome onto it, and it really worked, and people climbed over it, and it was finished, the head of the Ford Motor Company's engineering department said, I not only congratulate you, they've been very quiet with me, but he said, I'm going to dismay you very much to tell you what I'm going to tell you, but he said, we were so sure you couldn't do it that we had paid in advance. We paid the contractor because it was going to have to be done so fast. He required a premium. We paid him in advance. We paid the contractor to remove all your unfinished, no good work so we could go on with our show. We assumed it wouldn't be done. But so we're paying him much more than we're paying you for a very beautiful, successful job. Well, they really felt very conscience-stricken about it, and as a consequence, the Ford Motor Company went way out of their way to tell the Air Force, who were going on my radomes and didn't know, they couldn't understand why they seemed to work, and because the engineers couldn't calculate their work. The Ford Motor Company gave them to me terrific send-off, and that's one reason why geodesic domes really did proliferate so rapidly as a consequence of that project. Coming back now to the Napier developing a trick for the navigator. He got down to very simple devices. Assuming you still held on somehow to your tables and could look things up. If you couldn't, the navigator might know his mathematics well enough to know how you arrive at each of these calculations. That's a fairly simple kind of formula. You could get yourself within good sort of practical range, so you're within 100 miles where you are, possibly some case down to 10 miles where you are. Napier made this diagram, and incidentally, in trigonometry, if we're dealing sphericals, we draw a triangle like this. We put a little curvature in it, and you can see quite easily whether you're going to really is a 90 degree. I meant to draw that for a 90 degree corner, so this is a 90 degree, and this is corner is big C, this is big A, this is big B. And the side opposite C is little c, and this is little b, and this is little a. That's a standard convention in trigonometry. Then Napier developed a diagram where he had big A here, big B, and so this would be little a here, and this would be little b here, and this little c here. Then he put a complementary little c of modifying those three. This is his basic diagram. If you can remember that diagram, that's all you really need, so you never get into trouble. Because then he said, I'm going to make a rather poor poem, but you can probably remember it. As I said, the sine of any part will always equal the product of the tangents of the adjacent, or use the word cosine, ops and cosine, they've made a rhyme out of, and tangents and adjacents they made a rhyme, equal the sine of the product. Sine of any part will always equal then the product of the cosines of the opposites or the tangents of the adjacents. If you remember that statement, it's not too difficult. The sine of any part will always equal the products, means multiplying the cosines of the opposites and the product of the tangents of the adjacents. And then I'll show you what it means by opposites and adjacents. So let's say this is 90 degrees, and you learned that the one thing you know is this is 30 degrees. So you can look up the sine of 30 degrees. No, excuse me. I'm going to say what I have known in my here. Maybe I know that's 30 degrees, okay, and I know that little b is 22 degrees and some minutes, whatever it is, 30 degrees and 20 minutes. So I know two parts. So what I know is little b. I know little b, and I know big A. Okay. I've got to find then something called ops. Well, they are beside each other. Therefore, I've got to get something opposite to it. So I can say the sine of little a, and every time I write little a, I've got to put the c above it. Sine of little a equals, these are ops, the cosine of big A times the cosine of little b, also putting a little like that. Now I've got my formula written out, and I've got to substitute where the c's occur. I've got to get that out of the thing. These are put in here so you can't make the 180-degree error. So then you convert the c, you revert to, so this instead of being sine has to be read cosine. Cosine of little a equals cosine of big A times the sine of little b, because this is the opposite of cosine. Now I've got a formula that I can look up my tables what the sine and so forth are, and I've got to multiply them. So if you also then have in those days we used to use logs, so you had the log of any of those numbers, and all you had to do was add them instead of multiplying them. So trigonometric tables were usually also given with the logs in those days. So you looked up your logs and you simply added or subtracted, whichever you had to do. It's fine. So this gave you then, by this time, so now you've learned what little a is, and you go on and find out with the other parts really very rapidly. This is a very fantastic, simple thing I've given you here. That's all there is to it. Now, there are many other formulas in trigonometry, I assure you. And there are special kinds of tasks to be done, and there are some really quite fancy formulas for doing it. But this is the essence. You can get today, Hewlett-Packard has a little computer, and that's now down to $350, or you can get a $750 one, but it has all the trigonometric function and everything on it, and you can do all the problems in this little computer. The $750 one, they now have programs, strips that you can put in, and so that there's something you did quite regularly, geodesic domes, just put in this 5 frequency, 4 frequency, alternate, and you get your answer just like wham, wham, what the length of every part is in the building. Once you've discovered then what the trigonometry is for the radius is 1, then I showed you here before you want to build a geodesic dome. And what I need to know is the length of a structural member. So what I really want to know is from here to here. I want to know the chords instead of the arcs. So what I do when I get what my angle is, I know then that the chord is 2 times the sine of 1/2 theta. So this is quite different. You can't just automatically multiply it and let's look up to a large angle. You can't do that, because I want you to realize the difference between because these things are. This would be the chord of that. That's not at all that number. So you can't just take. It's 2 times the sine of half theta. Just never kid yourself about that. So this one then I began developing what are called chord factors. The phrase has never been used, so I could give you, geodesic domes, I give you the chord factors for any radius, so all you have to know is your radius. And if you want, you can do it in meters or centimeters, anything you want. But so as people began to catch on what I was doing, then they found they could publish all the geodesic domes in various frequencies and the chord factors, and that's all I had to know, and you start putting it together as your dome. So I can tell you when I first did the first calculations for geodesics, there were no electric computers whatsoever. There were no kinds of everything had to be done longhand. You did have your log tables, and you did have rather poor tables. They didn't have the Edwards one. So it was very clear to me, coming at things the way I do, you're used to my kind of argument, that an omnitriangulated sphere, and particularly as it was tensegrity, was operative, but was simply going to make, because tension has no limit, therefore a tensegrity dome would have no limit, that all the arch domes had very limited clear spans, and St. Peter's was the largest in the world at the time of my first few days, 150 feet in diameter. And I looked at it, really getting some very large sizes. They're no longer building the domes with bricks and so forth, and having chains around them where you did Santa Sophia or St. Peter's, but they were doing what they call radial arch. They had great enormous steel beams running from the perimeter all the way up, which made a very long beam. The slenderness ratio had very heavy, and then they had a centering steel ring, and they were all brought to that centering steel ring. And the weights involved were enormous. Then they began to learn they could make them a little lighter, and then they began cross-triangulating. Well, this is what came out of my geodesics to the triangulation, so they began to find you can make those radios a little lighter by cross-triangulation. Anyway, my first calculations, I could see that the thing would probably work. And somebody, but supposing human beings had thought that before, the whole thing was doing calculations so things would come out accurately. It's not a game you could be just rough about. Things really would collapse. You know, errors would accumulate very, very rapidly as you went around the great circle. So, my wife inherited a little money this time. She decided to really help me buy time. We bought time, and I'm sure this is the reason why people had done it, because it was really going to take time. It took me 2 years to do the first calculation to really know the solve. And today, anybody with a computer, I mean, you really not run this out in a couple of, less than a half an hour, you knock out a dome. And nobody realizes the enormous advantage that has really moved forward to the man with calculating capabilities. And the computers carrying out tables to very many places and so forth. So that the accuracies are very, very great today. To me, one of the most interesting challenges here was that the calculating, if I hadn't done whole number, longhand work, I would not realize the significance in numbers. If you put it in the computer, just miss it, getting a simple answer. So I realized I really tended to make an exploration about the last moment in history where you would have the opportunity to really find something out, and that I'd better really pay fantastically strict attention all the way through here to the significance of everything as it went along. This kind of talk I'm having with you tonight, then, is to do with then what I call design science, comprehensive anticipatory design science. You deal with things sum totally in the terms of total resources, everything you know about the way the universe is working, how and why we have the energies available here, why there is a biosphere, and how you really then employ the resources of physical resources and the knowledge to the highest advantage for all humanity, and if possible to sustain all humanity for all generations to come. That is your challenge. And you must be responsible for how every way you participate in the transformations of nature, employing those principles. You must be responsible for how the thing gets where it's going to go. You must be responsible for how it goes while it's working there, and how you take it away, and how to get recirculation again. You must be responsible for the complete cycle. There's no point where you're not, well, whatever you produce is now melted up and being used by somebody else. But as far as you're using those resources, you must be responsible from beginning to end. I gave you a way of realizing yesterday in big patterns the metals that are occurring all around the earth, and therefore there's a halfway around the world you go to find them all, and they gradually converge till they get to maximum separation apart, then they get into reassociation in preferred ways, and then when they finally have such advantage for man to really justify such a big operation, you have to make them available to the most people around the world. So it means you have to send them halfway around the world again to make them available. So that's the size of the operation. And often really doing things the right way is much easier than doing it the wrong way. At any rate, I never find myself shuddering at the size of the problem, and every one of the projects that I have undertaken, and tomorrow we're going to go over a lot of the projects I have undertaken, were always undertaken on this kind of a basis, and all students who ever worked with me have learned how I feel utterly responsible all the way through to humanity for having tampered at all with all this extraordinary phenomenon we learn about. I show you this kind of carrying on is a very inspiring matter. It makes you tremendously conscious of everybody and why everybody's doing what they're doing at this particular moment. I can understand why they're preoccupied. I can understand the fears of that father about his kid's going to be able to eat, whether he's going to lose his job. I understand all those things. And so I feel very, very kin to everybody, not at all annoyed at non-cooperation. But you have to find out then how you get it done. And you keep at it till suddenly you begin to find there are ways of getting things done. Now, I've been giving you a few sort of clues of I'm always looking for the simplest also. So it's nice to get this thing out of the way. That's the language of words, and they should not feel formidable at all. It's a really very simple kind of thing, because that is a tangent line. And you can understand what is really cotangent. You can see that, all that. It's really very self-explanatory. The only word, sinase, see, this is the withoutness, the openings. It is really to do with angles, how much the angle is open. You can see that, that's a very nice measure, because it's in the central angle. I think that is enough of talking about that diagram and talking about Napier. And I'm now going to switch over to tensegrity structures, because all the geometries that I have been identifying for you in the terms of topological analysis and volumetric analysis, energy analysis, quantum and so forth, all of those geometries can be made tensegrity. And so I point out to you also, one of the things that inspired me very early in the game of structures was getting into the push-pulls and how they're accomplished, and finally got I went over that with you, that compressions had limited lengths in relation to cross-section, and tension didn't. We went into all that, discovering that the universe is actually designed with islanded compression, usually spherical, as the most effective use of the energy that way, and the whole thing cohered tensionally. And the tension is the compressions are inherently discontinuous, and the tension is inherently continuous. We have a universe of inherent continuous tension. And that was not the way man was building. But when I found all the geometries and all these interrelationships, all this coordination, I was looking for nature's own coordinating system. I was sure it was rational due to the chemistry, and I found the rational coordinating system, and I found then that all the geometries could be produced in tensegrity. I was looking for this, and then I had the word. At Black Mountain College, I was a visiting professor the summer of 58 and 59. I was a summer dean. And there was a student there in 58 and 59, both, Ken Snelston. He'd been in the Navy, and his father was a photographic camera store man in Oregon. And Ken had he's fantastically expert in cameras, moving pictures and still, but he had a real feeling about art, and he liked painting. He'd come to Black Mountain and encounter his painting and to study with Albers there. And Ken Snelston fell in love. I talked to him, gave my energetic geometry. He was absolutely in love with my energetic geometry. And he was incredibly good at model making, so that for a whole year after Black Mountain, he came to New York or wherever I was and worked with me. And I went out to the Institute of Design in Chicago, and Ken Snelston moved out to Chicago. Then, in the second summer at Black Mountain, Ken showed me a sculpture he'd made, and in an abstract world of sculpture, what he had made was a tensegrity structure. And he had a structural member out here, two structural members out here that were not touching the base. They were held together, they were in tension. And I explained to Ken that this was a tensegrity. The man I'd found had only developed tensegrity structure in wire wheels and in universal joints. Universal joints where he had a steel shaft, and the reason for needing a universal joint because you're changing the angle of the drive, and you had two shafts, and each one of them came to three arm points like this, tetrahedrally like this. They had forged members, steel, and came to a pad with a hole in the end of the pad. So there are three pad holes, tripods like this, and they would bring those together at 60 degrees from one another with a flexible disc. And they would try all kinds of fabrics and leathers and so forth to see how long they would last. They would then rivet these onto that flexible disc, and as they drove this way, the disc would accommodate In other words, it was a tensional interconnection. The man had used tensegrity in this drive shaft of the universal joints. It also made it with a wire wheel where he had an island of compression of the hub and an atoll of compression of the rim, and the whole thing was tensionally coherent. So that this is the only place I found man who'd actually a tensegrity. So when Ken Snelson showed me this little extension thing he did, it was really just an arbitrary form. He saw that you could do it, and but he was just, as I say, an artistic form, something sort of startling to look at. And I said, Ken, that really is the tensegrity, and it's what I'm looking for, because what you've done, I can see it relates to the octahedron, and this gives me a clue how this goes together, all the energetic geometry. So Ken opened up my eyes to the way to go into the geometry. And Ken himself is an artist, and he's going on to make all kinds of tensegrity sculptures that are getting to be very well known as one of the most in the high demand artists. But Ken himself kept himself alive by doing moving picture work. He had got a moving picture cameraman's union card, and he turned out to be really one of the best. So he would, any time he wanted to work, he'd go and make a whole lot of money on some big project, and then go back and commit himself to his artwork. At all times in my carrying on, I have come to phases where I could see that something might be attractive from an art form. Continually get insights. I suddenly see new patterns that people see, and this could really be extremely interesting. I know personally, I'm deeply moved by it, that I could exploit it by stopping just being an artist. But that was my commitment. I told you last night. My whole commitment was to be absolutely responsible, to never exploit for self, and never just for self or fame, and you must not exploit. And if people try to make you fancy, then you must do everything you can to be sure that is deflated. So that I've never gone off of these forms, but it is interesting how many. I have an enormous number of artist friends, and they're really deep friends, and they're very simpatico what I do. And they do then go off, and they like what I can find out also technically, which gives a chance to do various things. And it couldn't be a more beautiful life than I've had with my artist friends. But I cannot talk about tensegrity without talking about the fact that Ken Snelson really was a catalyst to my discovering how I really connect this up with all the geometry and all the coordination, everything I want to do, doing more with less. And so I'm now going to go into the tensegrity with you and give you a little feeling. But I also did, earlier in that time, talk to you about pneumatics and tensegrity, showing you how and why it did get into regularities it did. So we don't have to go into that, and you'll recognize that as we go. May I have the first picture? Here I am also pointing out to you that where we have a balloon or a football or somebody said, they think about it, it's impervious, but if you look at it with a very fine microscope, it's full of holes. The only thing is the holes are smaller than the molecules of the gas that are inside. So they're really like a fish net, where the fish net is smaller than the fish, so the fish simply hits the net. And I saw them really operating very much as fish, the molecules of gas hitting the bag, and they're hitting it so many places, give it whatever its stretchable shape is, it takes that shape. So you can make strange-looking balloons of special shapes, because it's always getting pushed outwardly. Next picture. Then this represents, look at the upper right-hand side, or middle right-hand side, but I gave you the two swimmers coming together and shoving off from each other, and then hitting, going caroming off the, and there's no line that you can make inside there, unless it's a radius, that wouldn't be a chord. It could be a very deep chord, or it could be a very light chord. And if I'm really going around like that, hitting the skin a glancing blow. Now, because the two of them, action, reaction, shove off from each other, and they each hit the skin a glancing blow. The fact is then that a chord, an arc, it stays in the circle, but the chord, the center of the chord is nearer the center of the circle than its ends, so its ends are always emerging, hitting the skin at a very small angle. and there's a net of the two, one going this way and then both pushing out, really means a single force going out like that. And the magnitude of that force is governed a great deal by that angularity of this. But there's a frequent enough episode, it keeps it all moving out. So you can get the bag harder by putting more gas in, so that increases the frequency of the hitting very, very, very greatly. Next picture. Then I showed you how that what seemed to be the randomness automatically worked itself into the circles and the harmony triangulation. And the hexagons and the pentagons are simply incidental to the triangles here. The triangles are here. These are the spaces between the triangles do all the stabilizing. Next picture. Now the simplest, could that picture be dropped or turn it sideways? Can we go to it sideways? The simplest thing you could do for tensegrity is two members like that. Have the one that's bowed like this and the other bowed like that, a precessional effect, two coming together. These are very much like take a tetrahedron. I got two balls and two balls that's coming like that at each other. Or let's take a tetrahedron, consists of four triangles, or pair them into two diamonds. You take two diamonds and precess and come like this and grasp each other. That's exactly the way you make a baseball. And a baseball skin with two lobes in it, like our tennis skin, is really two of those balls. It is each lobe is a triangle of a tetrahedron, which you can then also draw as a circle, and then have the between the two complement that same radius. So you have two pairs of triangles, and two pairs of triangles, precess that come like that and grasp each other. That's your baseball. Incidentally, your baseball, if you draw it, is quite interesting because it is this. Is yin-yang. Yin-yang are these two complements, not in a plane, but really in the universe. And the baseball form is exactly this uniform radius all the way through this lovely thing. Baseball is telling you precession. It's telling you, the yin-yang to me tells me a great deal of I'm sure the Chinese thought in the terms of the whole too, and they came to a flat representation, but I'm sure they were thinking this way. And so they really felt the power of that yin-yang, so the complementaries do precess like this. Okay. So in this first one here, you can't take two straight sticks like this. You can if you want. And they are two edges of a tetrahedron. It makes a very flat tetrahedron. All you have to do is to have one tension member go right around. You call it a kite. You can make a diamond-shaped kite. You don't have to fasten these two to each other because it's simply a very flat tetrahedron and push it. By tighter you make the perimeter, the tighter this comes against it here. But it doesn't have to be fastened. It is the beginning of tensegrity. So it's a two-member tensegrity. So the two-member tensegrity is really then a precessional affair. But there's a little set of arc, a little like this. But the pull of those lines will make them do this little to each other. That's what that model is that I have there. You can see how you can take a ship now, a Naga ship with great ends, and the ends come out of the water like that. And you could have a spar going like this in the sky, which you then supported from the ends of that spar to the ends of the ship here, and out the other end of the spar. That's the other end of the ship is sticking out of the water quite far. Then you have to have a tension, fore and aft tension, to the top of this thing so it wouldn't fall over. It'd be quite possible to make a boat that way, and I'm surprised that people have not built boats this way, because it would be possible to drop sails from this thing is just connected in tension. I think we probably will see just such a device one of these days, because we'll get into very, very lightweight. Instead of having a mass that has to go vertical like that, This is a very much lower thing, yet can drop you a great square still, give you an enormous amount of sail. Well, okay, anyway. That's the simplest tensegrity. Next picture, please. The next one is one where you make the octahedron. You have the X, Y, Z coordinates, and I suggest you try this someday, and before you put tension from the end to end, you take some little box, say cubical box, and you tape one of the tubes onto it. The box has 6 faces, so we go another face here, and I have one going that way, and I have the X, Y, Z coordinates fastened onto the box, but a little away from each other. You understand that? Taped on. Then you take your tensions, omnitriangulate that, the 8 triangles at high tension. Then you remove the box to the center, and you find they just don't touch each other. So here we have very clearly the non-touchingness of the octahedron. And it makes it quite possible that with a little mild bowing by the tensioning to make them quite fairly accurate. We find in nature all the crystals that are octahedron or whatever they may be always they're askew one way or the other. They're always turbining the one way or the other. Now this was turbine. There are 2 ways of turbining this. May I have the next picture? No, I haven't come to it yet. This is a 4-member. I had 3 members, now I have 4 struts. This is this is a tetrahedron made by Ken Snelson. It's really very fascinating tetrahedron. It's a 4-strut tetrahedron. And it relates then to the vertexes and the opposite faces. You have a suspension of the opposite face. Next picture. I'm showing that a second time just to give you a little familiarity with it. Next picture, please. Now here's a tensegrity tetrahedron with 6 edges, 6 struts instead of the central angles which Ken Snelson uses, pushing out to a tension perimeter. Here we have the perimeter of the compression members. And we find that they again turbine, as you found it did just in the octahedron. There's a fundamental turbining. It can be positive or negative, but turbining you're going to have to do. And so it's good fun to make this tensegrity tetrahedron. And this tensegrity tetrahedron, you can slide the compression members on the tension member on that. Next picture. Now I have 2 tensegrity octahedra. One is positive and the other is negative. You can see them there. One twist positive, the other negative. Next, and then I bring the 2 together. Next picture. And they make then the 2 pairs of parallels. You got 6 of them. There were 3 in the 2 octahedra. One was positive and negative. They come together and give you then this balance, both positive and negative. It's a very, very stable form. And it has 6 members, therefore 12 ends. And the 12 ends are exactly congruent with the 12 vertexes of an icosahedron. So this turns out to be an icosahedron. And you can see connecting other tension members from the ends that are not connected, how those triangles could all be completed. Next picture. On the right then I have 6 members in the form of the tetrahedron. And the second one, I'm sliding the compression members along on the tensions towards their centers. They get to the center and they become the octahedron, and on the end the same 6 become the icosahedron. So you see same 6 quanta. Remember, 6 compression with quanta, 1 unit of quantum, 6 same quantum. 1 quantum is being either the tetrahedron, which is the simplest structural system in the universe, or they can be the octahedron, which is the next, and the icosahedron. But the icosahedron, remember, gave us the most volume with the least energy investment. The tetrahedron gave us the least. It was the stiffest of any load against any vertex. Much more trouble to push on the tetrahedron where the tripod is steep than when it's flat. It gets down a little flatter, easy to push it in. So that the tetrahedron has the greatest strength with the least volume of the 3 fundamental structure systems in the universe, and the icosahedron has the most volume with the least surface. So that You decide exactly which you want. In fact, I decided I would take icosahedra and fortify each of the local triangles with local tetrahedron. So you take those local high lows, and that is exactly really the design of that Ford motor coming to dome. So it came out octahedron truss geodesic. Next picture. Now we get into multiples again. This is on Ed Applewhite's lawn in Washington, and this is the 30 strut tensegrity. And then it begins to multiply quite rapidly in higher and higher frequency. This is a 2-frequency icosahedral tensegrity. Next picture. That is the same thing. And this is one the model I made in Japan, because the Japanese became very, very interested in this. Next picture. That's the same. Next picture. This is a model I made of it also. Still is the 2-frequency tensegrity, but it's an extraordinarily delicate model made by the students for me in Ghana. These are little mahogany struts, and they did really excellent jewelry kind of work of connection. The tension connections are so delicate you can hardly see them. They same students then made me a 40-foot tensegrity sphere using mahogany. It was the only really good compression we had there, and we had to use fence wire, cow fence wire, to add it. But it had made extraordinary, and so it was much heavier than you'd like, being made out of mahogany. But it was a beautiful thing, and the students, I'll never forget when they really finished that structure. The engineering department followed all the way through. They sure it wouldn't work, and it certainly did work. It worked superbly. But when they finished it, the students ran with it across the campus, a flat central campus, with it overhead, and the shriekings and the callings out, they really went back into very early war cries. These are the in Kumasi, these are the most greatest warriors of Africa, and they really got that kind of exaltation as they ran forward this film. When they had it on the campus and did not tie it down properly, and they had a full hurricane about a month or so afterwards, and the hurricane really picked it up in the sky and quite high, and it came down as a bowl upside down and didn't hurt it at all. I assure you this made the engineers look at it all the more carefully. It was a heavy dome. And next picture, please. Now we're looking at I wish that could all be in the picture. This is a beautiful dome made by the students at the University of Oregon, and it is a very high frequency, and it is a great big one. At the moment that we're looking at, I think this picture is of me from behind me. Anyway, they had worked on, this was about a 6 frequency, and worked terribly hard on it, and it was a beautiful affair. It was higher than this room. It was a big sphere. And we finished it, and I said, this is pneumatics, and it will bounce. And I said, do you dare drop it? They've been putting this together, making it for 2 weeks, and so we're all holding it out there. It's very light. And so you really have to go along with your theory. So finally they said, sure enough, we let that go and came bust right back to our hands, right around. Next picture. This is a model at the University of Minnesota getting ready for what are called the geoscope by getting these miniature Earths, and I've talked to you about that before. And they were planning to have a 40-foot, a 100-foot miniature Earth on the campus at Minnesota, and this is the model we were making. It was tensegrity. It was a very exciting one. I'll show you photographs. I hope that I have them with me here. We've got into making the struts then in polyester fiberglass cigars. There were struts about 10 feet long, and using beautiful flexible aircraft cable, very high there's chrome nickel cable. We then made a quite large section of the actual 100-footer, And sure enough, it worked, and so there was great excitement on the campus about that. We did not have time to finish that, and again, I'm sorry to say, when my university projects, I go away, and the budgeting of different departments are poor, and when I'm there, I literally spend my own money on the project, and then they don't have enough money to carry on. So that thing got deteriorated. They had it in a field house for a few months, and then had to take it apart, and never got put together again. Next picture. The students at Princeton, this model, next picture please, they then put up this was a 40-foot diameter tensegrity on the campus at Princeton. Down there, the research laboratories of the architecture department, and you can see, I think, a man standing in the middle down there. It's a very big sphere. We had it hanging from 5 telephone posts we put in out like that, so it hung tension inside of that. And the amazing thing happened, because have you seen the even tensioning we have? Unfortunately, a lumber truck backed up into it on the far side, and what happened was the stress went all the way around on the side, 180 degrees from where the truck hit it. The strut bent. All the forces went completely around and focused in one point, like a radio wave. Again, a snowplow ran into it that next winter, and again 180 degrees away, another one got bent. So there were 2 bent ones up in the sky there. This dome brought a great deal of interest at Princeton. There was a time when Einstein was there, and I understand the old man went over and looked at it a great deal. And all the scientists said they were really very taken aback by discontinuous compression. There's another one which I'll show you here, which I had on the campus at MIT, and we'll be coming up in a little bit. Next picture, please. This is that one at Princeton again, and I think you may be able to see one of those bent ones up there in the far right middle side. Next picture. This is the largest tensegrity we've ever built, and that was at Southern Illinois University, and it was 72-footer, and it was a 12-frequency truncatable, as you could cut it off at 4 different places, as well as being tensegrity. Now, and you could do that on 6 different axi, where you could fractionate this in fractional spheres. As you see, as you get higher and higher frequency, the chord and the arc get closer and closer to one another. So the arc altitude continually decreases. As you get to a smaller central angle, the arc altitude will decrease. That's pretty clear. So when we get a high frequency, we get where just the thickness of the material of the strut uses up the arc altitude. So at Southern Illinois University, we deliberately, the mathematics for that 12-frequency truncatable were the mathematics done originally by the students of Kumasi, Ghana, when they produced a very extraordinary aluminum dome down there, which I'll talk to you more about, which is a beautiful self-cooling, a chilling machine, as they called it. That's the aerodynamics of it. Somebody made cold air inside. The hotter it got outside, the cooler it got inside. As long as the sun was shining, it worked that way. Now, the mathematics of that, which I found the Africans had extraordinary joy and appetite for mathematics. They had quite a few electric calculators there on the campus at Kumasi, Ghana. I had 70 students in my project there. And in an American project at the university, when I get the individual students to choose which team they'd like to be on, if they're on a function that only lasts a little while, then they can finish that and go on to another function. So they all elect which ones they'd like to do, whether they'd like to be purchasing agents, like to be public relations. Incidentally, all projects like that, you've got to have public relations. The world is going to ask you what it is you're doing there. And you've got to have a very, very well organized. So this is not just out of the world, it is the world. And the world is, you're fooling with the frontier of the world, of humanity. So it has great interest. There must be a very good public relations man and highly responsible. And supposing you are then might be on the mathematics team or engineering. In American out of school, out of 30 students, my average would be 3 or 10% would like to be in the mathematics team. In the Kumasi Ghana, the Africans, out of 70, 50% wanted to be on the mathematics team. They love mathematics, and they're incredibly good at it. When I hear Western world, white-skinned people talk about the dark-skins, if they did not have intellectual capability, they're a little slow. There are the effects of bad nutrition and so forth, but the point is that anybody's ever heard the drums of the different tribes of Ghana, and they do come together annually, these different extraordinary tribes, and with their different kind of drummings, and have beautiful tape recording made of them. Anybody knows the music they have in them, you understand how and fundamentally mathematically coordinate they are. It's spontaneous, and they just loved it. Anyway, they did develop this very complex 12-frequency truncatable, which we did use at Southern Illinois University. And we then, using the figures, came to what size, if you were using 2x4s, which is the most plentiful way in which lumber is produced, and if we used not free, highest strength 2x4s that are produced, which turned out to be there are two kinds. There's a yellow pine and there's an Oregon fir that have this high strength. And we then took the way in which the 2x4 dresses out is not 4 inches, it's 3 and 3/4 approximately, and not 2 inches, it's 1 and 7/8. And you take your dressing size. We then calculated what size dome, using 12 frequency, truncatable, would become where the arc altitude was exactly 3 3/4 inches, which was the way so that if you made it that way, see, in tensegrity, one strut goes over the other, one inside the other. Could we go back to one of those tensegrity struts? One before this, picture before it. You see a strut goes under another one like that. Because one goes through the chord height, and the ends are at the full radius height, so that the ends are always coming out above. So we found we got to just where the ends would be exactly 3 3/4 inches above the mid strut. Therefore, they would touch each other. Now, this is a very interesting kind of one, because in the tensegrity structures there is a little springiness of the tension. They are bouncy like that. I found then all we had to do our mathematics absolutely perfectly, and then you would have a hole in the middle of the strut. And we took these struts themselves and scarfed their ends. We had them then go by one another, like this, brought together, and a hole vertically down like this, and that hole came to the exact register with the hole in the mid-strut below it, where the two ends came above it. And everything was just where it wanted to be. No, there was nothing in shear. Everything was just where it wanted to be. Because in tensegrity, these parts are really being pulled apart. But we got to where this is exactly where it wants to be mathematically. It doesn't want to be any place in all the universe. Nature always wants to be most economic. She wants to be most comfortable. This is the most comfortable position to be in. So then all we had to do is have one vertical bolt going through those holes and make it fast, and everything wanted to be. And I've never seen a dome then going together with this one fastening at the one place it wanted to be, just hold it there. And this took dampened all the springiness, so it made a very firm dome. So next, may I come then? Yeah, you can see the ends being above the meshes. Next picture. So this is that 72-footer, 12 frequency. We bought a telephone pole from the telephone company and used it and hoisted it aloft as we went, and then the university said they're going to have to take it away, so I didn't take my pole out. The pole is not holding it up, obviously. But it was one of the most beautiful domes we ever produced. I'm sorry to say, Southern Illinois University campus plans, architecture planning system, we had to remove it. But it should have stayed there really as a permanent building of that campus. The students loved it. They climbed over it a great deal, like little kids would climb on in a park, but grown-ups are climbing all over this all the time. I think the university is also afraid they might get hurt. So one reason or another, they forced me to take it down. Next picture. This is one I said that was quite a famous one. I made those with the deliberately bent parts to go around like that. This is MIT, and I made it with chain and tubes, and we this is the very beginning of tensegrity. It's 1950. I was a visiting professor, had the graduate class in architecture for a term, and I put this structure on a landing in the main building of MIT. We come in Massachusetts Avenue, up on the second floor that you can walk up, and a lot of people walk up to the second floor. So I put it right on the landing halfway upstairs, and I'll show you. I've never seen anything quite like the MIT professors that saw this in a show that shouldn't be doing what they're doing. They were jumping over. It was try to use a trampoline, and it just stood up. And that year I was asked to speak to the faculty club at MIT. William Worcester was the Dean of Architecture at MIT that year, and a very fine man, Bill. And later on he went back to Berkeley, where he'd come from, and he became the Dean of the Architecture School, and he's the one who changed the name of the Architecture School there. Anyway, Bill Worcester was a big man, and he'd been asked to do this during World War II, and World War II is just over. And he, at a meeting of the deans of MIT, he said, I see that the faculty club does not think really very well of the architecture department. They think that we're the department of liaison with idiots. Somebody has to talk to the idiots, and then they feel they're all so sane. But he said, we've never been asked to provide the quarterly speaker to the faculty club. And so the other deans admitted they never had, and the Bill did have a point, so they asked him then to provide the next quarterly speaker. So Bill found that I was a good, he asked me then to be the quarterly speaker. And I brought that model, I actually made the model for that occasion. And after the luncheon, we put it up on that landing I told you about, and had all the consternation. Anyway, and being asked to speak to the faculty club, I really don't know how and why I got to doing what I did. Anyway, I said, I'm surprised to be asked to speak to you because you're all so ignorant. And they really all looked very surprised. And I said that I'll just prove it, because I showed them that they all knew that the Earth was not the center of the universe and so forth, but they were all still seeing the sun go up and down. They were all using words up and down that had no meaning. I showed them all the things they were saying that had no meaning. And brought a great deal of laughter, but they knew it really was right. But then I showed them this model of the way they built things, and then they didn't build things in tensegrity at all, and then the universe was doing things in tensegrity, and they were building things absolutely compressional, with absolutely no enlightenment at all kind of buildings. So I think they would like to have proven this thing didn't work, because I said they were really jumping on it, and it really carried the loads in a great way. Next picture. Now, going into, there is a central angle strut of a tetrahedron. It's not a regular, it is not a tensegrity, but it has tension around its outside. Next picture. I have that, you make a column of cubes, and you know that in every cube there is a tetrahedron. In fact, there are two tetrahedrons. There's one diagonal and the other, the red and the blue tetrahedron, each one. Next picture. If I then take only the red tetrahedron in each of the cubes, I'm going to put in make a tensegrity tetrahedron for that. Next picture. This is on its side in order to be able to get it in there, but you can see then I've used this business of these two come together. They've got tension between them. There's tension of a square. So this one then that has a pair going that way above it, and makes a square section all the way through. So you have tensions along the sides. Then also I found that I didn't have to have these. This didn't touch the other pair, because I found that the one above it could be tensionally slung within it. That's what you'll see the detail of here in a minute. Next picture. So it made it possible to make a mast. You can see the two of them. You see the pair going like that, and a pair like that, and they're just tension because they are being pulled the other way. So they don't touch each other. Yet they make these central angles of the tetrahedron, stretching out the 4 to 4 points, which would be 4 of the 8 corners of the cube. But then the corners of the cube are taken care of by the alternate ones. This one from here takes care of that corner, and the one coming from above takes care of the other corner, so that they get the square of section of each of those cubes. This made me my mast, my first tensegrity mast. I made one of those down at Black Mountain College, and then Ken got very excited. But this was it. From this point on, Ken himself made some better tensegrity masts. Next picture, please. This is the one I had in the Museum Mountain Art Garden. I think this is the one. Yeah. Next picture. This is another one down in North Carolina State, where we did not have the sling between the two. Next picture. And this one of Ken's, really very much simplified, is a 3-sided mast. And he simply continually turbines his members around, going up like that. Next picture. Then I saw that I could take any tensegrity, I could take any geodesic dome, and for every strut I could substitute a tensegrity mast. Then if I looked at that tensegrity mast closely, there was masts in it. There were struts there, so each one of those I could substitute a very miniature tensegrity mast. Then I get a super microscope and I look at the struts in that, and I substitute a tensegrity mast there. I keep that down and finally get down to the size of the atom. This way the atoms are. So it's absolutely compatible with the atoms. So I saw that. Please understand what I say, because the red aluminum I'm using is just tensegrity atomics anyway. That's exactly what that alloys are. I gave you the other day. Just critical proximities, and they're simply held in the intention of one another. So that this became very exciting to realize the compatibility and the rate at which you would continually approach. You're doing just what the atoms doing all the time anyway. So tensegrity was, as in pneumatics, you can suddenly see what the molecules are doing. You can see what the atoms are doing, and you're doing what they're doing. Next picture. Then I found you could make a, may I have that back? Then you can get into a solid matrix, go in all directions, and using the 2 pairs of octahedra that way. Next picture, where they don't touch each other. So you can have isotopic vector matrix in tensegrity. This is a picture made in Japan, where I made a steel tensegrity, and they were interested in one for a very large, enormous dome for the Olympics, which did not get built, but they went through a very powerful testing on tensegrity. You can see hanging from a joint, looking into those pictures carefully, you see some bags. Those are bags of sand. And they are continually hanging more and more of them on the joints, and heavier and heavier. Some they have a great many bags around that joint. Next picture. This is the board of scientists in Japan. The dome is in the foreground here. Next picture. And the workmen are inside with helmets. They keep adding on more and more of these bags and so forth. Next picture. They had total weight calibrating around the vertexes at all the points of support to see whether it's really distributing its loads even, and it was doing that entirely, and they could get the sum total of weights that are being added in, so what the cumulative weight was, and what they had electric strain gauges on each of the joints, so that we found loads were being absolutely evenly distributed, and then we got up to very, very, very high load, way over anything was necessary for that particular project. Next picture, next picture. This is a Black Mountain where we were doing that one of the 72-footer. And the students were making tests where we then used empty oil barrels and filling them with water was a very good way. You want to know exactly how much you're getting in the loading. And so all of our projects we test, we do not just guess. We make static load tests to be sure that we're not endangering students or the campus and so forth. So it's always had to be under responsibility as you go.